All right. Good morning, everybody. Nobody here yet, but hopefully people will join or watch the replay. So I saw an article the other day that I thought would make a great topic for a discussion, which is about nuclear power in space. And that term kind of evokes a lot of different imagery. Um, and I assure you, it's much less exciting than what you might be imagining based on science fiction or TV or movies. But it is a really important discussion that goes well beyond space exploration because, of course, it is nuclear material, and so we're going to talk about it. And I'm just looking for the screen share button here on the live panel, and once I find that, I will share the article. But until then, I mean, what we can basically talk about without the article is that when you're in space, you need power for your spacecraft, and there's really only a few ways to do that. One of them is with solar panels, and you can do that if your solar panels are going to be in the sunlight most of the time. Another is batteries, which you can use solar panels to charge the batteries, or really anything to charge batteries. Excuse me, but again, that requires either you need a very short mission like the first space missions, where your batteries that you launch into space don't have to be recharged and you can complete your mission, or you need a way to recharge the batteries, and that's either solar power or nuclear. And so um, people realized early in the space program that they would need non-solar options to generate electricity, and the timing was good because it was shortly after World War II when scientists in America had spent a lot of time working with nuclear materials, obviously, and so there was a lot of there were a lot of people working on the subject and a lot of active research going on. And so what what NASA decided on was basically using an isotope of plutonium 238, which is created during the process. Well, so originally it was created during the process of making nuclear weapons, um, nuclear material from the 40s. But now we don't have to make nuclear weapons to make plutonium 238. But the point is, it flowed directly from the nuclear weapons research of the 1940s. And basically, you have this radioactive material that is constantly emitting particles. And in the case of plutonium 238, that actually heats up. It's really hot. The thing is a chunk of it, as you can see in the article, in the image at the headline of this post. It glows red. It glows an orangey red, and that's because it's just that hot, like a coal. The difference being that a coal in a barbecue, for example, has to be lit on fire and then burns out eventually. But this nuclear material is itself on fire, which of course is not fire; it's nuclear decay. But that it will be hot for, well, for I think the half life was 80 years or something, like, yeah, 82 years. So it'll be hot for a while, and then it'll slowly cools off over time. But what the researchers in the 40s realized was that, and this is Wednesday, who's decided to join the live. Um, the researchers realized that that heat from that nuclear material could be used to generate electricity in space, and it could also just be used to produce heat. So um, there's two kinds of uses of this stuff that we'll talk about, and that's of course different from an actual nuclear reactor, which uses large amounts of decaying radioactive material to produce heat that usually boils water, and that steam moves a turbine, which generates electricity. So we're not talking about that. There's really not much nuclear reactor work in space, and that's not really the subject of this video. Rather, what has been done a lot is using this plutonium 238 material, using the heat that it continuously releases simply by the nature of it, by its nature as a nuclear material, um, to do one of two things: either heat up the surrounding area, which is like the um, it could be a set of electronics that have to be kept warm. I mean, it literally just uses the heat for heat. That's used in something called radioisotope heater units, which is short version RHU. So you see in the article, if I can ever manage to share it, or if you look it up yourself, that's one use of plutonium-238, and it's really just like a heater that lasts for a really long time. The other is something called a thermoelectric conversion system. So basically, you take the heat and you turn it into electricity, and that's sort of oversimplified. What's really happening is you have a very special material such that if there is a differential in temperature on it, there's a flow of electrons out of it, basically. So now, one nice thing about outer space is you've got a great supply of nearly absolute zero temperature. So if you have a very hot material over here, and you have vacuum of space over here, you have a huge temperature differential, and that's what was originally that's what made it possible to generate power in space in this way, where you have this thing called a thermocouple, which connects the very hot heat source of the radioactive material to the extreme cold of space, and so that creates your temperature differential, which is how which is where the electric current flow comes from. So that was the insight in the 50s that led to the development of this stuff in the first place. So that's called those things are put together in something called an RTG, a radioisotope thermoelectric generator. So like I said, it's basically really hot object, the nuclear material, really cold space, and a piece of metal, really interesting piece of metal in between, that when it has a large temperature differential across it, it produces electricity. And that's really it. That's been used in dozens and dozens of space missions. All of the probes that went past Jupiter, they used these things. The Voyager probes were in the news recently because they're coming up on half the half-life, or the past half the half-life of their age, rather half the half-life of the material itself. So if you design your spacecraft such that no matter what you do, after 40 years, your plutonium is going to lose half of its heat. Sorry, half of its heat, because its half-life is 80 years. So you better design your mission so you only need half of the energy that you had when you started. So that's basically happening to the Voyager spacecraft, in addition to them being very old. And so they're changing what the mission, this was expected, of course, but they're actually having to implement changes on what the spacecraft do. Now, getting a pretty stable heat source for 80 years is not bad. And of course, that is why we've been using plutonium-238 over all these years. Now, you may ask the question, well, where does it come from? What happens when we run out of it? And that really is the subject of this article. And quite embarrassingly, I cannot find in this panel how to share the article, and I'll have to figure that out before I do this again. I'm going to keep poking around for a minute here. Well, you know what? I think since there's no one here anyway, we'll just talk about it and not show the article. But basically, the question is, I started this discussion by saying how NASA began using plutonium-238 that was produced during World War II. Now, the U.S. was not the only country to produce plutonium-238 during World War II. Russia did some, the Soviet Union did some. And for the decades since, there's actually been a really geopolitically curious arrangement over the years where there was some sharing of this material in order to enable certain space missions. And around 10 years ago, when I was, well, let me go back actually and talk about where this technology is used. So you can think about all the space probes that went past Jupiter. So that's at least Pioneer, several Pioneer probes, both Voyagers, New Horizons, the Pluto mission, and more, I'm sure. But that's enough. Each one of those probes had these radioisotope thermoelectric generators on them to produce energy. And Cassini, of course, and Saturn, and the big one that went to Jupiter, which I really should know the name of off the top of my head. Galileo. Was that Galileo? Point is, if you're going past Mars, until very recently, you needed nuclear material to generate power. And you needed power to do anything. Hello. Hopefully, Wednesday is more interesting than the article itself would be. So we're going to keep going. So, and also the Mars rovers use thermoelectric generators in a different kind of arrangement, but the temperature on Mars is cold enough that you can still get that temperature differential. It's not 800 degrees anymore or more, but it's because the temperature of Mars is a little warmer than space itself. But so anyway, you need them on the surface of Mars too. Now you can use solar power also, but on the surface of Mars. But for large power loads like the rovers, they did use the radioisotope thermoelectric generators. So that gets back to the sort of more modern question of where do we get this stuff? What happens if we run out? And the simple answer is, is if we run out, excuse me, cat. If we run out, we can't do these kinds of missions anymore. Now, thanks, cat. I'll have to fix that later. So now it should be said that in the recent decades, we have sent some solar-powered spacecraft out to Jupiter, like the Juno mission, which had 3 very large solar panels. The reason is that at Jupiter, the power you get from solar panels is only 0.5% of the amount of power you get from Earth's distance from the sun. So you either need huge solar panels way out there, or you need some other way of generating power like nuclear or like radioisotope power systems. So the question is, where does this stuff come from? And I have to fully admit that I don't know the full answer to that, because I'm sure that is highly classified information. And if I did know it, I couldn't tell you. But it was interesting when I was working at JPL that we were involved in figuring this stuff out for NASA. And that was an interesting challenge because we certainly didn't have access to all of the information. So we had to kind of figure it out from non-classified sources, obviously. One other application of this stuff that I've read about is that there are some systems put on the bottom of the ocean that are powered by plutonium-238 because there's no light down there at all. So same idea, no sunlight, you need something else. But you get the idea that this stuff is really useful when there's no other source of energy. So basically what we did at NASA was 10 years ago was we would look at the publicly available information about the material and figure out how much all the previous missions used, and then subtract it and try to model what missions that could be going in the future, how much they would use. So it was basically taking an inventory and trying to create these possible future, or trying to model these possible futures where if this mission and that mission and then that mission happened, how much plutonium would we have left? How long would it take to start making more? And we'll talk about how it's made, which of course is a huge project and a very sensitive one because it's radioactive material. So that was 10 years ago, and this article came out last week, and it basically repeats the question. what how is the changing inventory of plutonium-238 going to affect NASA's space exploration options? And the numbers, the specific numbers, are less important, really, than the idea that this is yet another thing that requires kind of long-term planning on the part of the U.S. federal government, and uh, it does have kind of global implications because it is a sensitive topic, even if the stuff is really only useful for producing heat. I mean, it's not even terribly. I mean, it's dangerous to human health, but it's not even as dangerous as most of the other radioactive materials. Don't quote me on this, but I recall that if there was a piece of it in a room, it wouldn't actively hurt you because the particles just sort of bounce off your skin. Now the vapors are dangerous, so people have to work very, very carefully around it. But even the radiation itself is not actually harmful because it's just heat. Um, I believe it's beta particles, which are just, um, well, nowhere near energetic enough to hurt you in that way. So the point is that, and that's actually been an interesting, that's actually caused some interesting protests because when the Cassini mission launched to Saturn, it of course had several radioisotope thermoelectric generator systems on board, and there was sufficient kind of environmental outrage over it that the launch site was actually protested, and it actually almost delayed the launch, I think. And the concern was, well, what if this stuff blows up in the atmosphere? Um, and all I know is that the way that stuff is packaged, there's no way it would disperse, and even if it did, it would be such a microscopic amount that it wouldn't matter. You have to remember that there's tons of uranium in the Earth's surface. I mean, it's really not a hazard unless you're stuck in a room with it, breathing it. So the point being, though, that it's yet another subject of kind of ongoing importance in space exploration because it's really the only way to generate power way out there, and there really isn't anything that can replace it on the horizon. So if we want to be exploring, either past Mercury and Jupiter or anywhere the sun doesn't shine, like caves or what have you, it's a topic that we need to be able to treat as an organized society. So I think I'm going to end it here because there's no one here anyway, and I can't even show the article. So maybe I'll do this again. But hope that was interesting, and thanks for watching if you did.